Okay, Pre-Calculus 12, here we go. This is video 16 in our course content. Remember, you can find all the videos in the grade 12 playlist, and they're connected to the workbooks on my website at mrhurlard.weebly.com. So today we are going to look at radical basics. Now, we've talked about radicals a lot from grade 10 through to grade 12, and there are a few pretty important details to consider, and I'm going to touch on something quite pertinent here, okay? So something to consider, because as you move forward, you might get confused with a couple of these topics that sort of intersect. Now, the first thing is, what is the definition of a radical? So the definition of a radical is base value A underneath a radical, underneath the radicand radicand is the A, and then the radical symbol is the radical symbol, and then the n is the root, so it's the nth root. So usually what we're used to looking at is this stuff. And that's just a square root. And technically there's a little 2 as my index, but we don't write it. It is our one redundancy for square roots. Because then after that, you get your cube roots, and then your fourth roots, and your fifth roots, and your sixth roots. And these are all connected to rational exponents. So if you want a refresher on exponents, you can definitely check out the Pre-Calculus 11 page on radical exponent relationships. But there's an interesting distinction with respect to your index, but also with respect to your value of A. Because if we have an even indexed root, so if we have a square root or a fourth root or a sixth root, then your A value, when it is positive, we have two solutions, two real number solutions. And why, and this is the important distinction, is because if you have a number like 16, and it exists as 16, and then you take the square root of it, you end up with plus or minus 4. So technically, taking the square root of 16 results in the positive or negative value of the square root of 16, which is positive or negative 4. And the reason why I make that distinction is because if you're later on from now, if you're given a root like that, it is assumed that that is the positive version of your root. Otherwise, it would tell you it's the negative version of your root. So that's the difference between being given a root or being asked to root something. If you start with 16 and you root it, then yes, you get plus or minus 4. But if someone were to just say to you, for practical use, what's the square root of 16, you would default that to positive 4, because negative the square root of 16 is what gives you the negative 4. So just be aware of that as you look through some of your notes and you get confused as to why there's only one answer instead of two. But for respect to this, when you square root an even a positive value, you get two results. You get plus or minus the square root of A. And that's anytime you have an even index. Now, if you have an odd index, so you have a 3 under here, if A is positive, you have one result. And that result is a positive result. If A is negative, you have one result, but that result is a negative result. So why is that? It's because an odd indexed, it would be like -2 times -2 times -2. Well, that gives you -8. But 2 times 2 times 2 gives you +8. There's no scenario where you get both solutions. And that's the varying differences. Now, back to the A being positive here and an even number. If A is negative underneath the root, in the real number system, there is no solution to this. Now, in the imaginary or complex number system, there is, but we're not going to talk about that system. And then obviously, if A is 0, if you have the square root of 0, the answer is just 0. So that is what a root is, and the root connects to how many solutions you have. So solve the following. So in this case, you're given x squared, and you're going to have to square root it. So the act of doing that makes you square root the 1, which that's why you get a plus or a minus solution. So you get both. Now here we have a cube. In order to get rid of the cube, we cube root. And when we cube root a negative, that's allowed. Great. And we end up with x is -3. Now in this one, we have a fourth root. So we are going to take the fourth root of 5. And again, that produces plus or minus, but in this case, it's just the fourth root of 5. We don't have a beautiful number. You can estimate that, it comes out at approximately 1.5, but this would be your exact notation for that. If we're taking the fourth root of -5, well, that's not allowed. You have an even index and you got a negative underneath there, so that is where we say no solution. So that symbol means the empty set. There is no solution in my set of possible solutions. So it does not happen. X cannot exist here. You do not cross the x-axis. You'll see where that comes in when we get to polynomials. Now, when you have this one, though, and this one, both allowed, both varying scenarios, though. Here, sorry, not x, 5. You can't take the fifth root of 5, so that's just your answer, fifth root of 5. Here we have the fifth root of -5, and since it's an odd index, you can have a negative underneath. It just means your answer will be negative. So those are the different scenarios depending on what index you're dealing with. Be comfortable with answers that stay under the radical, because it's more exact than rounding it into a decimal. Obviously, in practical application, physics, you're going to want to round because you need a number you can compute with and round to. But in our work here, we're going to keep it exact to the root. So how do we graph radicals? So we're going to take our basic radical and we're going to transform it, just like we did transformations in section 2. So the thing with your basic radical, there's a domain restriction, right? We can't have negative values underneath the root sign. Most of the graphing we're going to do here is a index to radical, but you will see a couple higher indexed cube roots, fifth roots, but we're going to focus mainly on second root. And it's the same thing we did with our other transformations. That's my vertical expansion / compression, again, by a factor of a. If it's negative, remember that then it's a reflection, right? So this is all sort of refresh from section 2. If you need some refresher, watch your section 2.4, 2.6 videos. K is our vertical transformation, either up or down. B is our reflection of the x values if it's negative, but then also it is our horizontal stretch compression depending on the value of b, and remember that the b is the reciprocal. And then h is our vertical or horizontal translation, left or right. So we work these the same way we worked our transformations originally, and what we're going to do is we're going to look at the mother graph. So the mother graph of a root function, well, when x is 0, y is 0. When x is 1, y is 1. When x is 4, y is 2. There's our basic mother graph of a radical. Now notice you have a domain x is greater than or equal to 0. We can't exist in the negative because we can't have negatives underneath our root symbol. Now, what happens in this transformation? All of our negatives become, or all of our x values switch signs, because remember that negative inside means -1 times x, and all that is underneath your radical. So in order for that statement to be true now, any x value I plug in has to itself be negative. So we get a domain switch where all my x values now have to be negative because my x values have changed sign due to my reflection, but that is the reason why that occurs. So you exist in the negative realm of x, and you might think that doesn't make any sense because we can't have negative x values. You're right, it's the negative x value that cancels with the negative that's in there already to produce a positive value. Both of these have the same range. Your range, I'll do it in white here, both of these have the same range, greater than or equal to 0 and greater than or equal to 0. We're still in the upper quadrants of our plane. Now, what about this one? This is a transformation of my y values. So in this case, you take the root and then you multiply it by -1. So 0 is still 0. And then when x is 1, you get 1, but now it becomes -1. And then when x is 4, you get 2, but then it becomes -2. So you can see we get, point should be there, we get a reflection of our original, of our mother graph, this time in the x-axis. And then for the last one here, we have a double reflection. So we could, in essence, take this one here. All our y values change, but then so do all our x values. So we're going to end up over here. So our transformations rear their gorgeous head again, and we're going to apply them to our radicals, but we do need to keep in mind our domain restrictions. Here our domain is greater than or equal to 0, here our domain is less than or equal to 0, but here our range is now negative and our range is now negative. So you can see you get some things that change around. Now, what about horizontal and vertical? So remember, here we're happening inside the function, outside the function, outside the function. So these are horizontal, and then vertical and vertical. So we take our mother function, and in this case, we're going to shift everything to the right one. But if it still makes you uncomfortable, you can still just plug values for x, because in this domain, x minus 1 has to be greater than or equal to 0, which means x has to be greater than or equal to 1. So that means our starting point is now here, and we've been shifted, right? And then when x was 1, y was 1, so this time when x is 2, y was 1. And if you're picking values to plug into a radical to test it, pick values that plug into x so that the number underneath your radical is a perfect square. It just makes life easier. So for instance, I'm not going to try 3 for x because that would leave me root 2. And I'm not going to try 4 for x because that would leave me root 3. But I'm going to try 5 for x because that would leave me 5 minus 1 is 4, and I get 5, 2. So you can see my mother graph from here is now shifted all 1 over. And then this one, we're just shifting the other direction. When x is negative 1, we have 0. When x is negative 2 plus 1 is, x plus 1 on the inside. Negative 2 on the inside doesn't work, right? Because what's our domain restriction this time? This time we have x plus 1 has to be greater than or equal to 0. So now we get x has to be greater than or equal to negative 1. So we can't go any more left than that, and then we just keep working our way over. When x is 0, and then when x is 3, we're going to get 4 underneath. So boom, there is your horizontal that way. Vertical, again, dead easy, right? Do your root, add 1. So root of 0 is still 0, and then add 1, we're at 1. Root of 4 is still 2, and then add 1, we're at 3. Root of 1 is still 1, but then add 1, right? We've just bumped our graph up. So we're doing translations. But when in doubt, plug values in for x and solve. So our negative 1, I'm sure you can follow along. We'll end up here, and we will end up 4, 2 now becomes 4, 1. So we are doing vertical and horizontal translations for this example. And again, we have domain and range. So here my range is greater than or equal to 0. Here my range is greater than or equal to 0. But now here my range changes because I've been vertically transformed. My range is greater than or equal to 1. And then my range is greater than or equal to negative 1, where your domain has stayed the same. Okay, so what if we are doing horizontal transformations? Now, if you can't recall the mother graph, then by all means, pick values for x, plug them in. So here, mother graph is 0, 0, 1, 1, 4, 2. Those are my favorite numbers to use on this grid because I don't go past 5. Well, so if you think from transformations, you have a 2 inside your function, which means you're multiplying all your values, x values, by a factor of a half, which means x being 4 becomes a 2, x being 2 becomes a 1, x being 1 becomes a half, right? And our y values don't change. So your graph is going to kind of look like that. Now, if that's confusing, just pick values for x. And you'll notice when x is 2, my inner function goes up faster, so it's going to get steeper faster, which is why it looks like it's been compressed. So 2 times 2 is 4, root 4 is 2. Or when x is a half, 2 times a half is 1, root 1 is 1. So, and then 0, 0. So you can always plug in values for x to try, but you can also think of it with respect to your transformations. Here we have a stretch by a factor of 2, because think your original x value still has to produce, or your inner function still has to produce the y value of your original x value. And how do we get the original x value? Well, we multiply the original x value by 2, so that's why x gets multiplied by 2. So when x is 2, we have 1 under there. When x is 0, we still have 0. But then when x is 8, we would get 4 under our radical. So we'd be way over here at 8 before we get to 2. So you can see this has been stretched by a factor of 2. So you can see transformations pop up again and again. So let's kind of put this together now and see what we end up with, okay? So if you think about your mother graph, let me draw the mother graph on here. Boom, and then 1, 2, 3, 4, 5. So we're at 1, 1, we're at 4, 2, and we'll just stop there. Okay, there is your mother graph in green. What transformations have happened to this? Well, this is 2, and then again, in your function, you want to factor out the -1, because that gives you your horizontal reflections, or your it adjusts your horizontal translations. So this is our function. So what is happening to our y values, right? Our y values are being multiplied by 2, and then we are adding 1, right? So our y values, if we had a comma b, we're going to end up with 2b plus 1. And what is happening to our a values? Our a values are being reflected, so multiplied by a negative, and then we are adding 4. So that is what's happening to the values of your original point. Now, we have a domain restriction in our new function, right? Because our original function, we have your classic domain restriction there, which gives us a range restriction there. But with our new function, we've been bumped up 1. So our new range becomes that. And our new domain, well, x, we are not allowed to have 0 in here, right? So x has to be greater than or equal to 4. So we can't even start, if we were to just pick points for x to choose, we would start at x equals 4. So if you did that, you would go, okay, well, when x is 4, 4 minus 4 is 0, root 0, 2 times 0 plus 1, so y is 1. So you see you get a point at 4 comma 1. And then you would pick your other points and go from there. But if we look at it with respect to just our change in coordinates, we had 0 comma 0, and we had 1 comma 1, and we had 4 comma 2. Well, what happened? 0 comma 0. So your x value gets multiplied by a negative, and then we add 4, so we're going to get 4. And then our y value gets multiplied by 2, and we add 1, so 4 comma 1. And would you look at that? There we are. And then our 1 comma 1, well, the 1 becomes -1, and then we add 4. What do we get? We get a 3. And then, what else we got here? We have 1 gets multiplied by 2, and we add 1, we have 3. So now you might be looking at this for a second, you're going, hold up. How come this looks like I'm going the other direction? Well, because this was our original domain, sorry, that one, but I jumped the gun here on our new domain, because our new domain actually has to satisfy this, because before we factor that -1 out. And the reason why I make emphasis there, or this, we need to consider that negative, because you have negative x minus 4 has to be greater than or equal to 0. Because remember, with inequalities, if we divide this thing by -1 to cancel the negatives out, and we divide that side by -1, we have to flip our inequality symbol, which means x is now less than or equal to 4, not greater than. And our range is going to be greater than or equal to 1, because we vertically transformed up. So we get there, and then if you convert your 4 to, the x value gets to -4, and then we plus 2, we get -2, sorry, -4, 4 becomes -4, and then we add, 4 becomes, -4, and then we add 4, and we get 0. And then 2 times 2 is 4, plus 1 is 5. So we end up with a point there. So what does this graph look like? This graph looks like that. That is our transform graph. We have this as our low point, right? Low point of our range, and we have this as our rightmost point of our new graph. So you can transform your points. In the notes, I also transformed the point 9 comma 3, but didn't do that here. So you can look at it as respective transformations, or you can look at it as, look at your new function and plug points in for x, starting with your domain restriction. So here's another example. If we look at it for transformations, what do we have? Well, underneath here, we factor out a 2. We have x minus 2. So if we look at our domain of this new function, you can forget about the 2 this time because it's not negative. You just need to satisfy this, which means x has to be greater than or equal to 2. So if you're going to start by picking points, if you made a table of values, you could say, okay, I'm going to take x equal to 2. And when x is 2, you get 0 underneath the radical, so you get -1. So you get a point 2 comma -1. All right, and then what you do is you pick values for x that will allow you to get a perfect square underneath the radical. And if you have x minus 2 under there, well, the next perfect square to get to would be a 1 and then a 4. So how can we get to 1? Well, you'd have to get a half in the brackets. So you're looking at moving into the land of decimals, right? So sometimes picking points can get a little bit more challenging than you would like. I mean, we could jump right to root 4 underneath there. We can get to root 4 underneath there by picking 4 for our x value. Because when x is 4, you have 4 minus 2, which is 2, times 2 is 4. So then root 4 is 2, minus 1 is 1. So when you are at x equal to 4, you are at a y value of 1, but we have a negative out front. So you have x equal to 4, 4, so -2, and then minus 1, so you're at -3. So you can see that doing it point by point can get a little bit messy if you forget about negative values or you rush. So that's why being able to look at it with respect to transformations is very helpful as well, because this is the transformed mother graph. And what do we have? We have a factor of -1, so a reflection, and we also have a vertical translation of -1. So think about the points on your mother graph, and when it's a root, it's 0, 0, 1, 1, 4, 2, and then 3 or 9, 3. So if we do the transformations to our y values first, we have a reflection of the y value, and then we drop 1. So we go from 0 to 0, and then we go to -1. Then we go to 1 to -1, and then to -2. And then we go 2 to -2, and then to -3, and then 3 to -3, and then to -4. So you can see my decrease is actually by 1, 1, 1. Now what is happening to our x value? Well, we have a factor of 2 in here, which means we're multiplying our x value by a half, and then we are adding 2. So that's what we're doing to our x coordinate. So 0 times a half is 0, plus 2 is 2. 1 times a half is a half, plus 2 is 1 and or 2 and a half. So I wouldn't plot that point because I don't like plotting fractions, but you still know it's there. 4 times a half is 2, and then plus 2 is 4. And then 9 times a half is 9 over 2, so 4 and a half. And then plus 2 is 6 and a half. So again, let's check the next root. If we had 16 comma 4 from our mother graph, right? The square root of 16 is 4. Then we would have 16 times a half, which is 8, and then plus 2 is 10. So you can continue to work your way through there. The 4 would become -4 and -5. So plot this now. You got your 2 comma -1, we already have it there. Your 4 comma -3, we already have it there. Your 2.5 comma -2, so we'd have a point about there. And then 6.5 comma -4, so we have a point about there. And the transformations there make it nice and manageable. So if you're feeling really comfortable with your transformations, do your transformations. If you're feeling really comfortable plotting points and plugging in, you can do that too, but I strongly suggest getting yourself as comfortable as you can with transformations. So what about graphing roots with even and odd index? The important thing for this is your inputs. What can you input into a root while you have a domain restriction? So we looked at this. This is the mother graph. We just end up with a graph that looks like that, right? We have one side because we can't have negative values. The domain is x is greater than or equal to 0, and the range is y is greater than or equal to 0. But if you have a cube root, you can put negative or positive values in for x, which means our domain is all real numbers. So what that does for our range is it allows us to have negative outputs and positive outputs. So we actually get all real numbers for our range as well. So think about this. You can't only take positive roots. Think about taking positive and negative cube roots. So cube roots are 1 times 1 times 1 is 1, and then 2 times 2 times 2, 8, and then 27. So try those, but try both of their pluses and their minuses. So if you plug those in for x, if x is 1, we get 1. If x is 8, which is off my grid here, we get 2. So I'll just go 1 off the grid, we'd be there, right? If x is 0, you have 0. So that still exists. But then if x is -1, you have -1, because the cube root of -1 is -1, and the cube root of -8 is -2. So you actually get a cubic graph, but flipped on its side, because you can have both the positive and negative values of x that exist in there. So you can see that a negative index substantially opens up your domain and your range. If you have a fourth power, it's the same as having a second power. You can see we just get steeper, because what is the fourth root of a value now changes drastically, right? So obviously 0, 0, 1 times 1 times 1 times 1, but now you're doing 2 times 2 times 2 times 2. So the fourth, you need 16, and then 3 times 3 times 3. So your numbers get bigger faster. So you actually end up with values here at 0 and 1, but then you don't get your next point at 2 until you get to 16, which is like way over here. So you have a much steeper or a much shallower radical expression, but again, you have a domain of 0 and of 0, because we can't have negative values in an even index root. With a fifth root, this will be the same as a third root. Our domain and our range are going to be all real numbers, because we can have positive and negative values in there. But again, in order to be a fifth root, your numbers are going to be quite large. You still get your 0 and your 1, but then 2 is 32, and 3, I believe, is 3, 6, 3, 9, 27, 81, 243. So it takes a long time to get to a root for on down your x value. So you're going to be quite shallow as you stretch through, but quite compact at the very beginning, because you still have this relationship here. But then in order to get to 2, so 2 on your y-axis, you're going to be way, way out here at 32 and way, way out here at -32. So the shift is less drastic. In your notes, it might look like an extreme shift, but be well aware of the scale of the grid that you're looking at. On the slide here, we have a scale of 5, but on the notes, the scale is 20. So that's why the graph looks steeper. Be aware on both of those. Always look at the scale of your given grid. Now, let's graph another one. So rather than think, well, no, we can think transformations. If you think about the basic transformation, or the basic y equals fourth root of x graph, when x is 0, y is 0. When x is 1, y is 1. So watch the scale here. And then when x is 16, y is 2. So 16, 2. Okay? So that would be your basic. And if you think about your basic like that, you have coordinates. You have 0, 0. You have 1, 1, and then you have 16, 2, because 2 times 2 times 2 times 2 is 16. So what are the transformations that are happening here? Reflection in your y value, and then shift down. So we're going to end up with a y value of -2. We're going to end up with a y value of -3. And we're going to end up with a y value of, so 2 becomes -4. So your y values actually go down in order. But then our x values, what's happened to our x values? Well, they actually just get shifted to the right 1. So 0 becomes 1, 1 becomes 2, and 16 becomes 17. So how do we plot the new graph? Well, 1, -2. So 1, -2, and then 2, -3, and then 17, -4. So there is your new graph. Obviously, you have some new domain and range restrictions, but I'll let you handle those. So transformations make this a whole hell of a lot easier than just picking values for x. Here's one more. So in this case, we have a cube root, which means watch your index, because now we have values on either side. The mother graph of a cube root looks different. Remember, the mother graph of a cube root was like this: 0, 0, and then 1, 1, and -1, -1, and then 8, 5, 6, 7, 8, 2, and -8, -2. So that was our mother graph. So what does that look like transformed? Well, again, we have some points there. We have 0, 0, we have 1, 1, but now we have -1, -1. We have 8, 2, and we have -8, -2. So you got more points to try to make sure you end up in the right realm. So again, what's happening here? We have a reflection and a drop down 2 for our y values. So again, we're going to have -2, we have -1, -3. We're going to have +1 minus 2 is -1, and then we're going to have 2, -2, -4, and we're going to have -2, +2, down to 0. So we've got our new y values. And then what about our new x values? Well, again, our x values are just shifting 1 to the right, so that becomes 1, 2, 0, 9, -7. And then we can plot those, so we end up with 1, -2. We end up with 2, -3. We end up with 0, -1. We end up with 9, -4. And then we end up with -7 and 0. So we go. So you can see the shape is the same because we have no horizontal stretch or vertical stretch. We've just reflected and dropped and moved over 1. So again, translations will make your life so much easier than picking points and plotting them, but you can do that. Okay, so now here's the big message. What's the difference between these two functions? And this comes back to that whole, if you square root a number, you get positive or negative, but if the root is already existing there, it's just positive on the outside. Okay, that's important. So think about your y squared. You have this, y equals x squared. You have your classic, everybody loves parabola. All right, now what you're doing is you are rooting the x squared value. So in this case, you had a point at 0, 0, and then you had a point at 1, 1, and -1, 1, and then -2, 2, and, comma 4, -2, 4, and 2, 4. Well, what's happening now is we're rooting x squared. So we're actually going to take the same x value, but we're squaring it first. So if you have a positive number under there, it doesn't make a difference. But if you have a negative number under there, the negative number gets squared first, which gives you +1, and then you root that and you get +1 back. And then when you have -2, you take -2, you square it, you get 4, you get 2 back. So what you end up with is you end up with a graph that actually resembles an absolute value because we are technically taking the absolute value because we square the negative first. So we still have 0, 0, and we still have 1, 1, and -1, 1, but then we have -2, 2, and we actually jump off in a absolute value of y equals x graph. So there's an interesting pattern there. It keeps your graph from curving. It makes it two linear equations. And if you want to plug these into Desmos, you can play around and you can see the way where the root exists change. So have a little bit of fun with that, and you can just see the change and the shift of your graph. Now, we're going to check out another one. In this case, we are now doing we're square rooting a perfect cube. So what happens in this case? Well, let's look at x equals y cubed to start. So to start, you would have a graph that looks 2, 8. You would have a graph that looks like this. But herein lies an issue. Because if we are square rooting a perfect cube, we have a domain restriction on the rooting, which means we can't have a negative value underneath, which means we actually have to disregard the whole negative chunk of my mother graph. That does not exist once I put a root symbol over top. And essentially we are just rooting our outputs. So if you had 0, 0, it stays 0, 0. If you had 1, 1, it stays 1, 1 because the root of 0 is 0, the root of 1 is 1. But then when we get to 2, 8, well, now we have to root 8. And the square root of 8 is a little bit less than 3. So you're going to have the square root of 8, which is a little bit less than 3. So what happens to your graph is it actually keeps the initial, but then it's going to kind of drop and dip. And then when your x value is 4 or 5 cubed and then rooted, so like 5 cubed is 125, root that, you're going to get slightly over 10. So it just kind of peaks out as a slow one-sided branch because we cannot exist in the negative realm, because as soon as you plop the square root over top, you can't have negative values underneath. So none of these negative outputs from our original function are allowed underneath. So we got one more to look at. And again, think of it with respect to outputs in this case, because we are square rooting our outputs, we're square rooting our original function. So similarly to when we did absolute value and when we did reciprocal functions. Because if you want to graph this original function, well, when you have a, what's it called? You have a vertical translation down, so your vertex goes there. And then we have 1/2 in front of the x squared. So when x is 1, it becomes a half. So when x is 2, it's 4 because it's squared. And then 4 times a half is 2. So when x is 2, we're at 0. And we're at 0. And then you want numbers that are basically squares that are divisible by 2. So x equals 3 I'm not going to do, but x equals 4. When x is 4, you have 16 divided by 2 is 8, minus 2 is 6. So when x is 4, we're here at 6. And when x is negative 4, we're also here at 6. So there's just a sort of little crunch of the original graph. Now, we are not allowed to take the square root of negative outputs. So that means all of this does not exist in the domain of my rooted function. So those values are all gone from my graph. And we actually just start our new graph at that value and that value, because when x is negative 2, we had an output of 0, so we still have an output of 0, but now rooted. So remember, you're rooting all of your outputs. What's my output here? My output was 6. So root 6 is a little bit more than 2. So when x is 4, we're now just slightly over 2. So here, and when x is negative 4, we're slightly, because you're rooting your outputs, right? You're rooting your y values. So this graph looks like this and like this. What you get here is you get a domain with a restriction that the domain is greater than or equal to 2, but also less than or equal to negative 2. It does not exist in this space in here, no domain. And your range is greater than or equal to 0. So radicals can be fun, a little confusing. I strongly suggest you have Desmos nearby so you can kind of practice on inputting and then seeing what happens, but definitely make sure you can graph them yourself. And I recommend just working your way through and enjoying yourself as best you can, right? What an easy thing to say. Enjoy yourself doing math. Okay, thanks so much. Remember, notes are on mrherlar.weebly.com, and you can always drop a comment if there's something in particular you need to see. Thanks so much, and I'll see you next time.